All right, welcome back, Physics 30. So I think this is the last video. We should be able to fit this all in. So interesting things with that time dilation formula. The person that's at rest compared to another object experiences more time. So space travel, time dilation has aroused interesting speculation about space travel. According to classical or Newtonian physics, to reach a star 100 light years away would not be possible for ordinary mortals because a light year is actually a distance. It's the distance that light travels in 1 year, which is a really big distance. Considering how fast light travels, 3 times 10 to the 8, it travels this many meter sticks. So if you shine a laser beam, it would go this far in 1 year. So even if a spaceship could travel close at the speed of light, it would take 100 years to reach such a star. But time dilation tells us that the time involved could be less. In the spaceship traveling 99.9% the speed of light, such a trip could work. So here's how you would have to do it though. You'd have to work it like this. So if we had, so our equation here, delta T is equal to delta T naught over 1 minus V squared over C squared. Okay, you know what that is. Now, so 100 years, according to the person of Earth, would pass by. So we would see that spaceship traveling for 100 years to reach that planet if we had binoculars. But how much time would be experienced by the person on the ship? If we rearrange this equation and solve for delta T naught, multiply each side by this factor, okay? And so 100 years passes by for the person on Earth, and the person on Earth would see us traveling for 100 years. 1 minus 0.999c, and we need to square all of that and compare it to the speed of light. So if you were to compute that, and you can do that with your calculator, this is mind-boggling because only 4.47 years passes by for the person on the ship. So that is interesting. 100 years pass by for us, but only 4.47 years pass by for that person on the ship. That is amazing. Thus, time dilation allows such a trip, but the enormous practical problems of achieving that speed would be very difficult to overcome. When we talk about spaceships moving at speeds close to the speed of light, it's for understanding and for fun, but not realistic. Although very tiny elementary particles, we can move particles at the speed of light. We haven't yet determined how to move bigger objects at the speed of light. So in this example, 100 years would pass by on Earth, but only 4.5 years would pass by for that person on the ship. Is it just that clock slowed down for the astronaut? No. So if you take a look here, all processes, including aging and other life processes, biology, would run more slowly for the astronaut as measured by the person on Earth. But of course, to the astronaut, time is normal. Biology is normal. I age normal. But to someone on Earth, they would basically see the person on the ship, everything moving in slow motion. That's what they would see. But to the person on the ship, oh, everything's normal. And of course, that is extremely weird. It's really mind-boggling to think about that. So the astronaut experiences 4.5 normal years of sleeping, eating, reading, and so on. But the people on Earth, they experience 100 years. And if they were to look in the spaceship, they would see us moving at a snail's pace. And of course, this brings the twin paradox into effect here. So not long after Einstein proposed the special theory of relativity, an apparent paradox was pointed out. And we talked about this earlier. According to the twin paradox, suppose one pair of twins are 20 years old. One takes off in a spaceship traveling at a very high speed to a distant star and back again, while the other remains on Earth. So we can think of it as they're on Earth, and this twin, he's taking off in a spaceship, and he's going this way. All right? So according to them, he would get old, and I would see him being younger. Okay? So they travel back, and the one on the Earth could be 40 years old, whereas this one here could maybe just a year pass by for him. Okay? So the paradox part of that is this. Remember we talked about, well, things are relative. This is the viewpoint of the twin on the Earth, but what about the traveling twin? If all inertial frames, highlight that, that's the important part. If all inertial frames are equal, can't the twins say that, oh, you know what, actually it's not me that's moving, it's you on the Earth that's moving away from me. I could just say that I'm standing still. So won't the twins say the same thing? And yes, guess what? For a point in time, they will. Old, and you're young because you're the one that's moving. Therefore, you're the one that's aging slowly compared to me. So how in the heck could that be? Which twin is going to be older upon arrival? So that's the interesting part. And they both can't claim the same thing. One of these has to be right and one has to be wrong. So can't the astronaut twin claim the same since the Earth is moving away at high speeds? Time passes more slowly on the person on Earth, and won't he age less? So they can't both be right, for after all, the rocket returns to Earth and we can compare the ages and we can compare the clocks. One of the viewpoints is indeed incorrect. The consequences of special theory of relativity, remember Einstein's relativity case in point, is that the situation can only be applied to inertial frames. And in fact, there's only one inertial frame in this scenario, and it's the Earth. The person on Earth is always, we could say they're always at rest. They're not experiencing any movement whatsoever. Whereas here, this person has to accelerate, speed up, speed up, speed up, reach the speed of light, then slow down, slow down, slow down, turn around, speed up, speed up, speed up, slow down. So he is not in an inertial frame. This person is in an inertial frame. So it's the inertial frame that is the correct one. And that's the best way we can describe that sort of thing. The person that's in the inertial frame will be correct in his or her observations. So the spaceship accelerates at the start and end of its trip. When it turns around and the far part of the journey comes back. But again, part of the time, there will be that conflict, that conflict or the differences in what they see. And it is true. But during the accelerations, the twin in the spacecraft is not in an inertial frame. Therefore, she or he cannot use the special theory of relativity to predict their ages. So the Earth twin stays in the same inertial frame the entire time, and therefore that observation is the correct one. So there's no paradox there. The prediction that the Earth twin makes is the correct one. So that's the interesting part. You have to be in an inertial frame. And this may seem, oh, it's hard to believe that this happens, right? But guess what? GPS systems, airplanes, cars, boats, hikers use global positioning system receivers to tell them quite where they are. There are more than 30 global positioning system satellites that send out precise time signals using atomic clocks. Your receiver compares the times received from at least 4 different satellites, all whose times are carefully synchronized to within 1 part of 10 to the 13. By comparing the time differences with the known satellite positions and the fixed speed of light, the receiver can determine how far it is from each satellite and thus where the Earth is. It can do this to an accuracy of a few meters, and they've been constructed to make corrections due to relativity. And a few pages ago, we also talked about the planes example, in which clocks were sent on planes, clocks stayed on Earth. The clocks stayed on Earth, the ones in the planes went around the world a few times, accelerating, decelerating, and those clocks that were originally synchronized to each other, there were differences upon arrival. In other words, the clocks on the plane seemed to be going by slower than the ones on the Earth. So yes, time dilation, a very interesting and abstract concept, difficult to understand, but really, the equation is quite simple. You could do these calculations for a multitude of things because it's that easy. All right, so we'll leave it there, folks, and we'll see you again.